believe it or not, we're almost done with this AC chapter. So let's go on. And this is mostly terminology. So here's our phasor representations of the current, of the voltage, and of the impedance. And the impedance is given by V over I, and that's this calculation right here. So you get an impedance and a phase angle of the impedance. And remember, that's dependent on frequency, as we found out earlier. Units are ohms, just like resistance. It uses the phasor notation, but it's just a complex number. Two components, the real part of it and the imaginary part of it. Resistive component, reactive component. Reactive being the capacitor or the inductor. And the magnitude from complex numbers, the root r squared plus x squared, and the tangent being the rise divided by the run. The the tangent of the angle being the rise over the run. Okay. Specific elements. Now this is a review of what we've seen before. That the voltage and the current have this relationship to each other. For an inductor, voltage is J omega Li. For a resistor, voltage is R times I, just like DC circuits. The first line is just like DC circuits. The capacitor is, voltage is given by 1 over J omega C. That quantity, the reciprocal of J omega C, times I. Impedance is 1 over J omega C in the case of a capacitor. Impedance in the case of the inductor, impedance is J omega L. Okay. Admittance is just the reciprocal of impedance. So KVL and KCL still work. That we can talk about individual voltages, and they're going to be given by a magnitude and an e to the j omega t plus theta component. So let me pull up a pen. Red is pretty good. Or green. Anyway, there we go. So here's a green pen. So yeah, each individual voltage here given by a magnitude and the sine and cosine components given by Euler's number e to the j omega t plus theta. And they have to sum to 0. There we go. KCL, similarly, current is given by a magnitude and the e to the j omega t plus phase angle component. Just different symbols, just to kind of remind you that these could be very well be different numbers. Current might have a phase difference between voltage. Very probable it does, and as a matter of fact, in AC circuits. So for evaluating KVL, we can factor this out and write it in our phasor notation. All three numbers in the phasor notation. Current, similarly, very similar type of analysis. We can factor out the j omega t's, e to the j omega t's, excuse me. e to the j omega t's. And the problem is reduced to algebra. That's why we do this. Because we take a complex variable differential equation and reduce it to algebra. And we all know how to do algebra. Okay, some of the rules we've developed for resistors apply to impedances. So series impedances, just add, simply add. The equivalent impedance over here is the sum of the individuals. In parallel, in a parallel circuit, the sum of the reciprocals is equal to the reciprocal of the equivalent impedance. Just like resistors in DC circuits. Okay. So here's an example. We have these three components and 60 hertz. I'll go. So let's see how this works out. There we go. Write down the impedances for the three components. And they just sum. So here we're substituting for the omega, 60 hertz, 60 times 2 pi, or 120 pi. The impedance of the inductor, the impedance of the capacitor, impedance of the resistor is just the resistance of the resistor. Phase angle. V in its phasor representation, the magnitude and the phase angle. Magnitude, phase angle. Okay, putting it all together, we get, crunch the numbers, add the impedances together, so that we get, this becomes the impedance. So the voltage is the current times this equivalent impedance, series, ZS for series impedance, since all the components are in series. Current is V over ZS, 50 angle 30, 50 angle 30. And this is not in the phasor notation, this is just a complex number notation, but it's just crunching numbers. You can convert back and forth. We had the formulas to do that. The magnitude would be the square root of 25 squared plus 45.5 squared. The angle, the tangent of the angle would be the 45.51 divided by 25, which is approximately, let's see, tangents 2, that's about 70 degrees, and it'd be negative 70. There we go, negative 61.2. My head's not as good a calculator as a real calculator. And then, of course, from here, you divide these. These are magnitudes. They just divide. And you take this angle, subtract the negative 61.2. So we got an angle pretty close to 90 degrees. There we go. Positive 90 degrees. Is it capacitive, mainly capacitive, or mainly inductive? That's a question I want to pose to you. Let's see, Z. Pretty much it's capacitor dominated. There we go. The voltage is positive at a positive 30-degree phase angle. The current is 61.22 degrees ahead of the voltage. Leads the voltage by 61.22. For when voltage is 30, total phase angle is 91.2. Okay. Pretty much we've gotten through all the material for this chapter. We're just going to do learning examples from here on, and I'm going to stop this video here, and we got to talk about admittance just a little bit, but other than that, it's pretty much learning examples.